So on page 129, some more of the PVA problems, position, velocity, and acceleration. There's one vocabulary term in here that I don't think we've spent much time talking about. The word is displacement. And displacement is just where you end up minus where you start. Kind of like how far away are you from where you started and in what direction. Okay, so displacement, just like velocity, has direction, and again, it's just you start one place, you end at a different place, and therefore you have been displaced by a certain amount. And for problem number 2, it gives us a position function where t is greater than or equal to 0, t in meters, or s in meters, t in seconds, and it's asking us for the displacement in the first 5 seconds. In other words, from where you started, where'd you end up? Okay, well, you start actually at position 2, and I think that this is could be wrong, but it's probably you've got a moving particle, something that's moving along an axis, along a line. Okay, so this particle is moving along a line. Its position at time 0 is 2. The position at time 5 is 12. So if I were to make a little chart here, if I just actually draw a number line, if you start here at, let's say that's position 0. If you start here at 2, okay, so let's just give it right there. That's that time t equals 0. And then you end up 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You end up over here at time t equals 5. That's t equals 5. I need that other one. T equals 5 right there. Okay, well, it's just kind of like, well, how far is it? Well, how far it is from 2 to 12 is 12 minus 2, and that's 10. So that's 10 meters. Okay, so that's why the displacement in part A, the displacement in the first 5 seconds is 10 meters. Okay, so that's a picture of it. If by chance, you might be wondering, what about the displacement? What if we had started here at 12 and we ended here at 2, then what would the displacement be? Well, it would be 2 where you ended up minus where you started, so that's negative 10. Okay, so if you started at 12 and you ended at 2, the displacement would be a negative number. It would be negative 10 because you're 10 to the left of where you started. Okay, well in this case, we are not 10 to the left, we are 10 to the right. So let me erase all this stuff. Okay? And that's why the displacement then is 10 meters. Okay, let's go to part B. Part B is average velocity. And average velocity is really, really similar to average speed. Speed is always, though, positive. So average speed would be always a positive number. Okay, well, average velocity would be the displacement. So displacement could be negative, so your velocity could be an average of a negative number. But in this case, you just have to divide your displacement, how far you are from where you started, divided by how long it took you to get there. So your average velocity, and if you remember the concept, it's rate times time equals distance, as I wrote right down here. Rate times time equals distance. What we're really trying to find here is the rate, the average rate, and is the distance divided by the time. And distance, though, from where you started, divided by the time it took you to get there. And so that's 10 meters, which is the displacement, divided by the time it took you to get there. Gosh, did I make another mistake? Yeah, I did. I found it. So it didn't take you 2 seconds to get there. It took you 5 seconds to get there. Okay. And let me just check. Yeah, during the first 5 seconds. Yeah, so 10 divided by 5 would be it's not 10 divided by 2, it's 10 divided by 5, which is 2 meters per second. Okay, so I'm glad I caught that. And again, I've got to change it right down here. So you can see what happens to me at the end of the day, making video after video. The brain sees things differently and kind of talks without thinking. So anyway, it's good if you're catching my mistakes. It's good. It means you're paying attention. And all right, so that's part B. Let's go on to part C. Part C, we see that we're being asked to find the instantaneous velocity when t equals 4. Well, the velocity is the rate of change of the position, and we see that that's 2t minus 3. Instantaneous velocity at t equals 4 is the velocity at 4. So 2 times 4 minus 3 is 5, and that would be meters per second. Part D, acceleration is a constant. We can see that the acceleration at time t is 2 regardless of the time, so it's constant. That's going to be 2 meters per second per second. And then part E is asking us to find at what values of t does the particle change direction. This is good stuff to know. At t equals 3/2, well, changing direction means that the velocity either is negative, then it's 0, then it's positive, or vice versa. Okay, so when you solve v equals 0, you're not done yet. You don't know really that it's changed direction. I mean, really, typically it does change direction at that time, so you usually get away with it. But I mean, if you think about it, a particle could be going velocity positive, it could be going to the right, it could stop, velocity equals 0, and then it could keep going to the right, velocity positive again. So it didn't change direction. Now, typically, like I said, though, in problems like these, when the velocity is 0, that's the time it changes direction. But you just have to be careful. That's not enough of a reason for something to be changing direction just to say the velocity is 0. Okay, so you set up a little chart. You can figure out to the left of 3/2 seconds. From 0 to 3/2, you just plug in any value into that velocity equation, and the velocity at any time between 0 and 3/2 is negative. And then the velocity after 3/2 is always going to be positive. And so therefore the particle, in fact, did change direction at that time, and that's the whole reason, because velocity went from negative to positive at that time. Part F, I didn't finish this, so I'll finish it now. Where is the particle when S is a minimum? Okay, so we'll first have to figure out where is the particle at any time. So at t equals 0, at t equals 0, let's look back. The particle S of 0 is 2. Okay, so if we look at our position function, we see that at that time, right there, time equals 0, the position is 2. Okay, well, we see that the velocity is negative. Okay, we know the particle is at 12. We've already talked about that, by the way. The particle is at 12 way over here at the time t equals 5. Okay, so again, we know that to be true, but and your first instinct might be that it went from t equals 0 to t equals 5, it went to the right. That might be your first instinct. But if you combine what we're just talking about now with the fact that the velocity is 0, from t equals 0 to t equals 3/2, then, well, that means that the particle is actually moving, and I'll draw that in red, it's actually moving to the left when between t equals 0 and t equals 3/2. And so we have to figure out, well, where is it at the 3/2 mark? Okay, well, that's what we want to know. If we can figure out where it is at the 3/2 second mark, then we can figure out where it is when S is at a minimum. That will be at its minimum point, because it has to get all the way back there. It has to get all the way back there to position 12 at some point. We just want to know where is this here when t is equal to 3/2. Okay, so if you're really kind of staying with me here, understanding functions, we know that S, I'm going to erase some of this so I have some room. We know that S depends on t. So S, depending on t, is equal to, and that gives we were given that, t squared minus 3t plus 2. Well, we really want to know what the position is when the t is equal to 3/2. And so we get 3/2 squared, so I'm running out of room here, minus 3 times 3/2, okay, plus 2, which is equal to, and I'm going to have to cheat on this one, I'm going to look at the answer key, but that will give us our number. So I'm going to pause the video and get right back. Okay, so when you simplify this expression here, 3/2 squared, in other words, s of 3/2, you're going to get negative 1 over 4. And let me write that in green. Negative 1 over 4 meters. Okay? And so it didn't go very far, and I kind of overshot my my position here, because here's 2 right down here on the number line, and then negative 1/4 though is right here. Okay, so negative 1/4, that's really where it is. And so I'm going to erase this guy here and erase this guy here, and we're going to put that here. So it's going to go t equaling 3/2 is right here, right there. T equaling 3/2 is right there, and the position of the particle is right there at negative 1/4, and that's when the particle is at farthest, when s is at a minimum. It's farthest to the left. Okay, so that's a lot going on there, but it's a super important type of problem that you can to be able to answer. If you can answer this problem, then you can really handle just about anything I throw at you on the test. But be able to explain it though. Be able to understand the movement of the particle along a line, where it is at a certain time, what the velocity is at a certain time, whether the velocity is negative or positive, and what that means. So really seek to understand this, because this is where you, it's where students really have a tough time when they just try to memorize the process instead of understanding why and how it all works together. In fact, the last thing that this problem didn't ask was, when is this particle speeding up and when is this particle slowing down? Okay, well, as we see, the acceleration is always positive, and so we can see from t equals 0 to t equals 3/2, the acceleration is positive, but the velocity is negative. So just to do one more little thing here, the acceleration is positive and the velocity is negative from t equals 0 to t equals 3/2. And we didn't need this part here. Okay, so to t equals 3/2. So that would mean that the particle is slowing down when the acceleration and the velocity are working against each other. However, we can see that, let me do that in red as well. We can see that when t is greater than 0, we can see the acceleration is positive, but also velocity is positive when t, or I should say when t is greater than 3/2. That means the particle is speeding up. So I added one more thing to this, in which this is kind of like the last thing you need to know for these kinds of problems, as far as understanding them completely. And they're really fun problems when you kind of finally get it. It's very rewarding to be able to explain the entire process using derivatives. So hopefully you're finding as much enjoyment in doing these problems, besides the fact that it's taking time out of your day. But I think they're much more fun, these kinds of problems, versus just finding derivatives. That's just my own personal opinion.